How's everybody doing? Great. Okay, we'll go ahead and get started. All right, so what we'll do today is we'll finish off chapter 1 and talk about that a little bit, and then I'll talk about the quiz, give you a little information on the quiz. So remember, we're not having the quiz today on chapter 1. We're going to have it on Wednesday, and it'll just cover chapter 1. Once we get finished with chapter 1 today, then I'll start on chapter 2, but that won't be covered on the quiz. So, okay? So we left off, we were about to talk about significant figures. The key thing about significant figures is that when we're in a chemistry lab, we're making measurements, we're doing calculations based on those measurements, and we want to make sure that the results that we report are really reflective of the level of accuracy that we can expect based on the types of measurements we do. Depending upon who you have for the lab, they may or may not have shown you this, but the people who had me, I pointed out how along the glass windows, there were 2 types of balances. There were 4 kind of shorter balances on the left, and then 3 kind of bigger balances that had kind of like a glass enclosure on them. And those balances have different capacity in terms of total weight, but they also have different accuracies. The ones on the left, the lower ones, are called top loading balances. And if you look at those particular balances, you got 3 digits past the decimal. The other 3 balances on the right, the ones with the kind of glass enclosure, those are called analytical balances, and those particular ones give you 4 digits past the decimal place. So depending upon which of those you were using to do your weight measurement, you would have different numbers of significant figures because the top loaders aren't capable of getting to that 4th decimal place that the analytical ones were. So if you're weighing something that's pretty heavy, that 4th decimal place isn't that important, so you wouldn't worry about it. But if you're doing, say, making analytical standards where you're using a small amount of material, that would be important. So you would want to reflect that difference in accuracy in those measurements. And that's where significant figures come into play. It's all the digits that we have total confidence in, and then the last digit, which we're pretty confident in, but we know there's some error built into that based on the type of measurement instrument we were using. If you think back to that example of measuring the width of the coin, we had 2 different rulers, and one ruler had more graduations in it, so we could get an additional significant figure in that. So those 2 measurements, even if you're doing the same measurement, the accuracy is slightly different on those. And that's what you're trying to communicate with significant figures. You want to accurately express the accuracy. You don't want to claim something that really isn't there. And that's really the reason for significant figures, is to make sure that the data you're generating is truly representative of the quality of the measurement that you did. So So there's significant figures that we'll talk about that are linked directly to that measurement. And then we'll use those numbers to do calculations. And we'll talk about how the calculations impact what that final significant figure count is going to look like on our measurement. So just some general rules about significant figures. All non-zero digits are significant. Zeros between non-zero digits are significant. Zeros at the beginning of a number are never significant. Zeros at the end of the number can be significant if a decimal point is involved. We'll have some examples of that. So here are 3 examples of similar measurements, but with different significant figures. So the first one, 1.03 times 10 to the 4th, why does that have 3 significant figures instead of 2?
Because it's the 1, and then since there's a 1 in front of the decimal place, you count the numbers past the decimal place as well.
Right, that the 0 in that one is this one, basically number 2. Zeros between non-zero digits are significant. The next one, 1.030 times 10 to the 4th, we're saying that has 4 significant figures. Why is that last 0 significant?
Because of number 4.
Yep, because of number 4. Zeros at the end of a number that contains a decimal point, in this case it's 1.030, that is significant. And it's the same reasoning on the last one, 1.0300. So what that's telling us is that even though those are zeros on those second 2 examples, and so essentially you could say, well, the number is the same. Well, yeah, technically the number is the same from a mathematical perspective, but from a chemistry data quality perspective, we know that this last measurement with 5 significant figures, that we must have used a pretty good balance to get that. So that has 4 past the decimal place. So that tells me that you probably used one of those analytical type balances that give you those 4 decimal places. So we're really confident that about that first 0 after 3. We're pretty confident. The next one, we know there's some error in that.
Wait, I have a question about the first and the second one again.
Okay.
So wait, why is it 3 significant figures again?
So the first one is 3 significant figures because we have 1.03. So the 1 is significant. The 0 is significant because of point number 2, that zeros between non-zero digits are significant. So that 0 is between 1 and a 3, so 2 non-zero digits. So that makes that 0 significant, and then 3 is significant also.
Okay.
And then, I'm sorry.
Oh, it's a problem if the number ends in a 0, which is what the second one's come from. So it's 3 in that one, but it's, oh wait, no, it's 4. Okay.
Yeah, the next one is 4 because that last 0, it's in something that has a decimal in it. And this is one reason, remember we talked before about scientific notation? This is one of the big advantages of scientific notation, is it allows us to express that last 0 as significant by using scientific notation. If it wasn't scientific notation, we really wouldn't have a way to express that one as 0. And then the last one, again, with those last 2 zeros after the 3, we're in scientific notation. We have that decimal there. So that decimal basically is number 4, where we're saying if you have that decimal there, then those zeros at the end become significant. The decimal is the key. Does that make sense?
Oh, wait, okay. Sorry. Just a little confused.
That's okay.
So if the decimal is there, it makes the number significant, is what you're, is what
It makes those last zeros significant, is what it does.
Oh, okay. So, all right. I just need to look at it again because they all have decimals. So I'm just trying to grasp it. Sorry.
So like if it had 3 zeros at the end, like let's say it had 6 significant figures, like how long does it go until it stops with the zeros at the end? Like for forever?
So it would go for significance, would go based on the measurement device you had.
Oh, okay.
So if you had a measurement device that could give you all those zeros, so for instance, on balances, I've seen balances that go out to 5 places. I don't know if I've seen one that goes out to 6 places. So in other words, that many decimal things past the decimal point.
Oh, okay. I think I understand what you're saying.
Yeah.
So
So
it's after the decimal. We're not counting the whole number. We're not counting that.
yeah, we're looking at, so just to repeat, on the last one, the 1 is significant because we said all non-zero digits are significant. So that tells us the 1 and the 3 are significant because neither of those are 0.
Oh, gotcha.
Then we got to figure out, are the zeros significant or not? Because we said from our rules, sometimes they are, sometimes they aren't. The first 0 is significant because it's between 2 non-zero digits. It's between the 1 and the 3. So that tells us it's significant. The next 2 are significant because of point number 4, that zeros at the end of a number are significant if it contains a decimal point. So that 1.0300 has a decimal point in it. So it tells us that those last 2 are significant by definition of point number 4.
Oh, all right. Gotcha. I got it now.
Okay?
So I understand that like the zeros count if it's on a balance, but what if it's on like a calculator, and calculators can go for like infinity, so.
Yeah, so that's something you want to be careful of. Just because the calculator or the spreadsheet gives you all these numbers, it doesn't mean you use them. That goes back to, you have to look and see how the measurement was done, okay? So if you're in the lab, say you're in the lab this week doing some measurements, whether it be volume or weight or whatever, you know how you took the measurement. And whatever you use to take that measurement, you should know what the capacity was in terms of significant figures. If it was the top loading balance, for instance, you know you're going to have some number of digits before the decimal and then 3 digits after. So maybe you have 5 or 6 or whatever significant figures there, you'll get that. Then you'll use that value in your calculations, and we'll talk about some of those rules for calculations in a moment. But you'll use those rules associated with the calculation to help you determine how many significant figures should be in that final answer.
Okay.
So I think if you hold on for a moment, we'll have some examples of that, and maybe it'll be a little clearer for you.
Okay. One more question. Sorry.
Sure, that's okay.
Okay. So I know the test is already online. So, but just out of hypothetical, well, let's hypothetically say, do we need to memorize these just because we already do have access to the rules right here?
So I'll tell you what I said before, and I'll go in a little more detail in this when we finish the chapter, is the test is going to be timed. And so you're going to have a finite amount of time to do it. If you spend all your time looking everything up, you won't finish.
Yeah.
So the expectation is that, you know, maybe a question or two you'll need to look up. You probably have time to do that. But if you're telling me you're going to look up every question, I'm telling you, you're probably not going to finish. And then you're going to miss questions just because you never got to them because you ran out of time.
Okay. Just wondering.
Okay? Because basically, I take the test and I see how long it takes me to do it. And then I do some factor of assuming that I can do it quicker than you. Okay? So I don't expect you to be able to do it as fast as me, but I also don't feel that, you know, you should have enough time to just look everything up and not remember anything and all that. Because the reality is that some of this stuff, and some, you know, the first few chapters in this class, really, it's a lot of memorization is all it is. Later on, then we'll take the stuff that you learned and memorized and apply that. So you really want to get to where you understand some of this stuff so you don't have to look it up all the time. Okay, here's some examples of significant figures. Let's kind of go through some of these. So the first one, 0.00305. How many significant figures there? 3, because those first two zeros, we said any zeros to the left of the number don't count. So those first two aren't significant. Okay, 1.00. How many for that? 3 again, yes, because of that decimal, those tail end zeros count. How about the third one? 100. Is that 3 again?
1.
1, yes, 1. Why is it 1?
Because the zeros only count if there's decimal point.
Yeah, there's no decimal on that one. The other ones had decimals. And then 0.10556. There we have that 0 kind of wedged in between some non-zero digits, so everything counts there. So we have 5 there. And then finally, 2.050 times 10 to the third. That's similar to some of the stuff we were just looking at. So what do we think on that one?
4.
4, right. Because that last 0, as we said before, because of the decimal rather, is significant. So something like that, I would expect you to be able to do on the quiz or the test. You know, if you're given some values like that and then asked how many significant figures are there, you should be able to tell me. Okay, this is what we were kind of hinting at before, is what about calculations? So the rule in calculations is the least certain measurement limits the number of significant figures in the answer. And so what that means is if I do one weight and it has 3 significant figures, I do another weight that has 5 significant figures, that 3 significant figure weight is going to drive my multiplication, my division, things like that. If you're doing adding and subtracting, then it's the least significant decimal place. So in that case, if you're adding or subtracting and you have, say, 22.4 and 21.698, it's that 22.4. It would be the 0.4 would be all the further you could go in terms of significance on it, adding or subtracting. So in general, because anymore, most calculations are done on spreadsheets. You know, you guys will be using calculators during your tests and quizzes. So it's similar to that as well. But even on the calculators, you can chain a bunch of calculations together, okay? You typically don't do one calculation and write the answer, then do another and write the answer. You kind of chain it together. Spreadsheets, you definitely do that. So typically the way that's handled is you let the calculator, you let the spreadsheet keep all the digits as it goes through the calculation. And you don't worry about each step worrying about those significant figures. And then at the end, you go back and look at the measurements and determine what the significant figure should be from that. And then you'll do that significant figure rounding at the end of the calculation to reflect the quality of the measurements that you did, okay? Years ago, that was a lot of discussion about that. Should you round every step? Do you not round every step? And over time, the consensus has become you don't do that. You take all those. Sometimes people get confused when they use Excel, because Excel, you can set the number of digits that you see. The thing I will say, though, that means just because you only see 2 places past the decimal or something like that, Excel in its calculation is still using the whole string. So, all right. So here's a couple examples. So without worrying about the numbers, on the first one, we have 24.6 mils times 1.0567 grams per mil. If we do that multiplication, how many significant figures would you expect to use in your answer? 3, right. So, and that's based on the 24.6 mil measurement. We talked about this a little bit last class, but I see 1.0567 grams per mil. If I see grams per mil, what property is there a good chance that I'm measuring there? Density. Does everyone remember density was weight per volume, so grams per mil? And let me ask you another question. Is density an intensive or extensive property? Does anyone remember the difference between those two? So we said intensive, the I's link up. Intensive, independent, extensive is dependent on the amount you have. So with density, does it matter if I have a little cup full or a bucket full? Will the density change?
No.
No, it won't. So that tells me it's an intensive property. So in this case, someone had 24.6 mils of some substance that had that amount for its density, and they wanted to know how much it weighs. So this would be a common calculation that you would do associated with density. You have some volume, you want to figure out how much it would weigh. And this would be it. So the other thing we have going on here, and we'll talk about this a little bit more in a few moments, but is dimensional analysis. Remember, we mentioned dimensional analysis, which is how we convert from one thing to another. And so in this case, the mils units will cancel with the mils units on the grams per mil to give us an answer in grams. So we had a couple things going, we had a couple things going on here in this problem, in addition to significant figures that we can learn. We had dimensional analysis. We talked about density, density being an intensive property. So a few things going on in addition to significant figures, which if you do the math, 26.0 grams. So we have 3 significant figures there, right? Because of the decimal, that last 0 counts as a significant figure. How about the next one? We have a subtraction here, 4.6389 minus 2.1. How many digits past the decimal are we going to have in our final answer? Right, we're going to have 1, because it's that 2.1 gram value that kind of sets the tone for that, defines how many digits we're going to have there. And then finally, the last one is similar to the second one, 25.6 mils plus 27.81 mils. That 0.6, that 1 digit past the decimal on the first 25.6 mil value is going to determine how many digits past the decimal we have there. So when you start doing the calculations, whether it's multiplication and division or adding or subtracting, adding and subtracting rules center around how many digits are past that decimal point. And then the multiplication division centers around how many significant figures you have in the values that you're dealing with. Okay, any questions on that? Okay, let's talk a little bit about dimensional analysis. We had a brief example just now using dimensional analysis with density. So, you know, it's interesting in general chemistry, there's some things that you'll learn for the class and you probably won't use much as you go forward. There's other things you'll learn for the class that I guarantee you will use constantly if you do chemistry stuff. This is one of them. Dimensional analysis. This is the key to most of the calculations that you'll do. Remember, we talked about dimensional analysis as the process we use to kind of convert units from one thing to the other. And what you'll learn is that the formulas in chemistry usually have certain units that variables need to be in order for the formula to work correctly. And so a lot of times you have to do some adjustment to whatever your measurement was done in to get it in the proper units. And that's where dimensional analysis comes into play. So we'll talk about conversion factors. And here's one example. 1 inch equals 2.54 centimeters. So those types of conversion factors are what we use to convert from one unit to the other. The key to doing this correctly is to make sure your units are canceling out. If your units are lined up, don't even worry about the numbers, but if your units are lined up so you know that you're canceling things out, then you can go back and put the numbers in and kind of do the math, and you have a great chance of being successful and being correct. And so here's an example down at the bottom where they do a couple of conversions, and they want to go from meters to inches. So the first step was to go from meters to centimeters. And we see there the conversion factor is 1 centimeter is 10 to the minus 2 meters. So if you look at that, you have a meter on the left, there's a meter in the denominator, those meter units cancel, so now whatever that number turns out to be would be in centimeters. Then our next conversion is 1 inch is equal to 2.54 centimeters. So our centimeter units, once again, with 2.54 centimeters in the denominator, that would cancel the centimeters, and then now the final units would be inches. Then you'd have an answer in inches. So there you have a two-step dimensional analysis to go from meters to inches. It doesn't matter where you're doing something like this, meters to inches, or it's a volume, or it's a weight, or just whatever. The units are the key. So if you know that if you're in the numerator, then the next one, the unit you want to cancel needs to be in the denominator, and keep that kind of theory. If those units are canceling out correctly, then it's just a matter of making sure you put the numbers in with the right thing and then press the right buttons on your calculator. A lot of times, if you're a little confused about how to do a problem, you can actually figure out how to do it by just lining up the units, thinking for a moment about what units you're trying to get to for the final answer, and then seeing what units you start with. And a lot of times then you can piece together what the process is by just getting the units to work out. So dimensional analysis, you'll use it in this class, you'll use it going forward because it's really a key thing to learn. Okay, so here's an example of dimensional analysis where they're saying speed of sound is 768 miles per hour. And they want to know how many miles does sound travel in 1 week. So we want miles per week. The data we have says miles per hour. So the miles part, we're good to go. We don't have to do anything to converting the miles. We need to convert hours into weeks. So most of these we should know. So we know there's 24 hours in a day. So we see that hour in the 768 miles per hour, in this case with the hours in the numerator, day in the denominator, that hours will cancel and will be in days. Then we know there's 7 days per week. Once again, then the days cancel out and we're left with week. Finally, that gets us to miles per week in this value. So here we had another two-step dimensional analysis, but it goes back to, if I just ignore all the numbers and just simply look at the units and then line those up and see what cancels, we see that things cancel out to where we have miles per week. Does everyone know what I mean when I talk about canceling the units out? That just means that if you have something in the numerator, if you have days in the numerator and days in the denominator, for instance, they cancel each other out. If you don't have, so in this case, we have miles in the numerator, we don't have any miles in the denominator, so that miles unit has to stay in the numerator. And then for this example, there's no weeks canceling out, so we wind up with weeks in the denominator. So that same basic approach, that same basic idea of canceling those units out is what you'll do every time when you do a dimensional analysis. So the names change, the ratios change, things like that change, but the basic idea will always be the same, okay? All right, here are some additional homework problems that you can work on. The type of stuff you'll do here would be the type of stuff you would expect to see on the quiz or the exam. So that wraps up chapter 1.
This will be on the quiz too Wednesday?
Yep.
Okay, just want to know.
Yep. So the quiz Wednesday, and I'll talk about that a little bit here. The quiz Wednesday will cover all of chapter 1. So the stuff that we covered last week and then this little bit that we did today. we had this homework set, and there was another homework set of some example problems that I'd recommend you take a look at. And so that's what the quiz will be on. The quiz will be 15 questions, each worth 2 points. As I said earlier, there'll be a 15-minute time limit. And what we will do on Wednesday is we will cut the lecture portion short so you have time while you're in this class time period to do the quiz. There will be a defined amount of time that the quiz will be available. So it's not like you can, take it tomorrow night, Wednesday night or something like that. So the way this works, the quiz will be in Canvas. You'll log into Canvas, and then you'll have a period of time that the quiz is available. Once you start that quiz, the clock starts ticking on the 15 minutes. And at the end of 15 minutes, the quiz will end whether you're finished or not. And that goes back to what we talked about earlier, is that you should, if you look up everything, you're probably going to run out of time in the 15 minutes. But if you know the stuff and maybe only look up 1 or 2 things, you should be fine time-wise. So what I would suggest is, for those of you who are going to be in class, I would bring your computer with you and take the quiz here while you're here. Obviously, if you're online, you're logged onto your computer and you have that available and can do that at your house or wherever you're at. Any questions about the quiz? Okay, I'm going to pull up the other chapter 2 and start on that here. So hold on a second. Okay, can people online see the chapter 2 slides?
No, we can't.
You cannot, okay.
We can see them now.
Okay, can you see it now?
Yep. Yeah, we can.
Okay, thank you.
Thank you.
All right. So in chapter 2, we're going to talk a little bit about atoms, molecules, and ions. A couple things I want to say about chapter 2 is the first part of the chapter is more like a chemistry history lesson. So we're going to be talking about how some of the atomic theory developed, some of the people who were involved with it. What I would like you to take away from that isn't necessarily a lot of detail about how the experiments were done or who's who or anything like that. What I'd just like you to get an appreciation for is that this happened, long time ago, time before there were computers or a lot of the technology that we take for granted now. And so the people who've kind of figured this stuff out, it's really pretty impressive that they were able to figure some of this stuff out given the tools that they had to work with at the time. So that's one of the main things I'd like you to come away with from this. The other thing I'd like you to appreciate is that the way science typically works is rarely do people get it right on the first try. Is that just as we talked about hypotheses and theories and laws and all that earlier in chapter 1, and we said there was kind of a process of figuring stuff out and testing and going back and revising and all that. That's kind of what you see on display here of where people had ideas and they had hypotheses and theories and things like that, but then as it got tested, it would kind of fall apart and they'd make revisions and all that. So that's the other thing I'd like you to have an appreciation for in this, is that even this stuff that's pretty core to what we know, it was a process to get there. And it was one of those things of where now we look at it and go, well, yeah, everybody knows that. But at the time, no one knew this. There was a lot of discussion, a lot of argument within the scientific community about really what was going on. Okay, when we think about atomic theory, it goes all the way back to the Greek philosophers. And they believed that there was a small particle that made up all of nature. And this is where the word atom comes from. And so it's kind of interesting because obviously back then they weren't doing experiments and stuff like that. They just didn't have that ability. This was all just philosophy. But yet when you think about it, you know, they kind of had the right idea even back then. In the 18th and 19th centuries, then there started to be some experimentation. And there was a guy named John Dalton in the early 1800s who took some of the learnings from that experimentation and kind of combined it with some thoughts of his own to come up with his atomic theory. And the key there is they call it an organized atomic theory. So it's not that he figured all this stuff out himself. Some of it he did, some of it other people did. But he was able to look bigger picture and see how all of it kind of fit together to get one of the early atomic theories in place. And his was based on 3 key things. One is the law of constant composition. And remember, we talked about that last in chapter 1 earlier on. The other is law of conservation of mass. And thirdly, the law of multiple proportions. So we're going to talk a little bit more in detail about what each of those are. Constant composition, that law, as I said, we talked about last chapter in chapter 1. And if you remember, that's the one that says in a compound, there is the same proportion in the compound, no matter where you find it. So if we take water, for example, H2O, if it's truly water, it's 2 hydrogens and 1 oxygen. Doesn't matter if it's coming out of your faucet, if it's in a lake, if it's frozen, if it's vapor. If it's truly water, it's H2O. So any compound has the same proportion of the elements, no matter what. No matter where you find it, no matter how much there is, any of that. That's this law of constant composition. Law of conservation of mass tells us that if we have a substance and we have that total mass, and then we do some type of reaction, the matter is neither destroyed or created. So what that means is, if you have 2 compounds and you react them, and there's a certain number of, say, carbon, hydrogen, oxygen in each of those compounds, whatever is formed will have the same number of carbon, hydrogen, oxygen atoms as those starting materials did. So in other words, you can't come up with more carbon or less carbon or things like that with that reaction. And so matter changes. So if you do, say, a combustion reaction where you burn something up, you obviously don't have that material anymore because you've burned it up. But whatever it went to, if you were to capture that and analyze it, it'd have the same number of, say, carbon and hydrogen. So think of gasoline, for instance. Octane is one of the main components in gas. So you do that combustion. So you have the octane gets burned in the engine. Well, you haven't created carbon, you haven't destroyed carbon, you've just had it change forms. And so that's what conservation of mass is saying. And we'll see later when we do things like balancing chemical equations and things like that, that's the basis of all that work is this law, this conservation of mass. And then the third one, law of multiple proportions. It says if you had two elements, and we'll call them A and B, and they form more than one compound, the masses of B combining with the mass of A are going to be small whole numbers. So once again, using the water example, if you do something and you form water, it's going to be H2O. It's not going to be H1O a half. Okay, it's always small whole numbers. And so that tells us then that when we form a compound, whatever it is, that formula is always going to be the same, and we're not going to have partial numbers, half numbers, third numbers, things like that. So these three laws were the basis of Dalton looking at them and coming up with an atomic theory based on what he observed and others observed. Okay, so here's his theory. Let's talk about that for a moment. Each element is composed of extremely small particles called atoms. Okay, that sounds good. All atoms of a given element are identical to one another in terms of mass and other properties. But the atoms of one element are different from the atoms of all other elements. So all that means is every carbon atom, for instance, is the same. So if you have a carbon atom, it's going to have the same mass as the other carbon atoms, and it's going to have the same properties of the other carbon atoms. But the carbon is different than oxygen, or different than nitrogen, or different. So different atoms have different properties, different masses. But if it is carbon or oxygen or whatever, all the atoms that are that will have the same mass and the same properties. The next thing he said was, atoms of an element are not changed into atoms of a different element by chemical reactions. Atoms are neither created nor destroyed in chemical reactions. So this is kind of what we talked about, that conservation of mass. You have carbon, for instance, in a molecule in some form. You do the reaction, that compound maybe gets changed or destroyed, but the carbon itself is still there. It's just a different compound or something like that, but you haven't done anything to the carbon, for instance. So atoms are atoms. They represent an element. You do something to it, you don't change it to something else. Atoms of more than one element combine to form compounds, and a compound always has the same relative number and kind of atoms. So this goes back to us saying, once again, water is always H2O, 2 hydrogens, 1 oxygen. So there we're combining the hydrogen with the oxygen to get water, but that always is the case. It's always H2O. If it's not H2O, it's not water. So in general, you look at Dalton's theory and it's not bad. You know, especially you think when he did it, how long ago, and just what he was working with and all that. It's pretty good, pretty impressive. I'm sure that's certainly better than I would have done it at the time. So, but we know some things now, and we know that it's not perfect, that there are some gaps in this. So let's take a look at some of that and how they got to that. So one of the biggie for Dalton was, he said that the atom was the smallest particle possible. And we know now that that isn't exactly true, was not true. That there's something called subatomic particles. So these are particles that are smaller than an atom that we now know exist. And some of the key things are electrons, which was learned through cathode rays, radioactivity, and then the idea of a nucleus, protons, and neutrons. So we're going to spend a little bit of time talking about these things and talking about how they were discovered and just kind of what it means. But overall, Dalton's view was pretty good. He got us all the way down to atom level. It's when you go to subatomic type stuff that his theory doesn't hold up anymore. But all the stuff he said is true. It's just there wasn't enough detail there. So here we have a picture of a cathode ray system. And what I want to point out a few things. One is you see on the left, the negatively charged, the cathode is negatively charged in this diagram. The anode on the right is positively charged. If you look at the green thing in the middle, that's just some type of fluorescent screen that they have. And what turns out to be electrodes or cathode rays that are generated, they interact with that screen, and that's where you see the kind of streaks of light in there. So this was the setup that he did. So as these particles are generated, they move from the negative to the positive. Does anyone remember why they would move from negative to positive? We always say opposites attract, right? So the electrons, as we'll learn, are negatively charged, so they don't want to stay at the negative cathode. They want to move over to the anode in this case, because the anode is positively charged. So where that opposite attract thing is, if it's a negatively charged, it's going to move. And that's what you see. The other interesting thing about this is on the picture on the right, they hold a magnet up to it. And what is learned is that you can actually deflect these electron beam type thing with a magnetic field. And that's what we see there. You can kind of see it in the picture if you look closely. You see the light kind of bending upwards towards the magnet. So very interesting thing. And this is where they started to understand that negatively charged particles are going around. And that's what didn't fit into Dalton's theory. This is just another example of this. In this case, they have a positively, negatively charged plates there in the middle. They have a magnet as well, just as they had on the other one. And you can move the ions around based on how you apply that magnetic field and how you do charge those plates up. So by creating electric fields and magnetic fields, you can kind of move ions around. We'll talk about a few other techniques that leverage this kind of stuff to actually measure masses of ions and things like that. But for now, the big learning of this was that because of how they could move that around, they realized it's negative, the particles are negatively charged, and they decided to call them electrons. The other thing is, the guy who did this work, Thomson, determined that the charge to mass ratio of the electron is 1.76 times 10 to the 8th coulombs per gram. So that was important because now we're starting to get some quantitation associated with it. In addition to just saying, oh yeah, they're negatively charged, which was a big learning, he actually gave us this, well, what's the charge to mass ratio? If you know the charge to mass ratio, then if you can either figure out the charge or you can figure out the mass, then you can get the other one because you know what the ratio is. And that's where this guy Millikan came into play. And he determined the charge of the electron. So once again, it's one of those now where we all kind of take for granted that an electron is negatively charged, but back then they didn't know that, okay? Because remember, they were going off some theory that didn't even say that there were electrons. So Millikan did this oil drop experiment. You can look at that in detail if you want. I'm not going to go into it. But the big takeaway here is that Millikan determined the charge of the electron, and so that's where the negative charge comes from. Since he figured out the charge, then we could go back and apply it to that charge to mass ratio to then say what the mass is. Okay, let's talk about radioactivity a little bit. So this is a picture of Marie Curie. She's one of the early pioneers in radioactivity, her and her husband Pierre. Radioactivity is simply the spontaneous emission of high energy radiation by an atom. some atoms are able to do this, some are not. Some are radioactive, some are not. That's where you hear people talk about, is it radioactive? Not everything is, but some things are. What this did, the study of radioactivity showed that the atom had more subatomic particles and energy associated with it. So we went from Dalton saying nothing smaller than an atom to then finding out about electrons. And now the people who worked on radioactivity and discovered that found even more stuff that's subatomic. So there were three types of radiation that Rutherford discovered. One is alpha particles, and those are positively charged. The second are beta particles, those are negatively charged. And then there's gamma rays, which are uncharged. So two of them are particles, one is electromagnetic field, so with the gamma rays. And so we'll talk about that a little bit. What you see down here again is our old friend of electrically charged plates, positive, negative, and using that to kind of move things around. Once again, taking advantage of that opposites attract, same charge, there's a repel or repulsion type factor. And so what they're showing is they could pick out which were the negatively charged and which were the positively charged. So the blue one going up is negatively charged because we have a positive electrically charged plate there. So negative wants to go up there. The red one at the bottom is the positively charged. It wants to bend down towards the negative charged plate. And then the one in the middle, the gamma rays, that didn't do anything because it doesn't have a charge. So applying those potentials to the positive or negative plates doesn't do anything to it. So you see some common themes here of using that whole opposites attract, same charge repels type of thinking to move things around and investigate some of this stuff. Okay, what I'd like to have you focus on here are the definitions of ionizing power and penetrating power. So ionizing power is the ability of radiation to create ions. Penetrating power is the ability to pass through material. And when we look at our three types of radiation, the alpha, beta, and the gamma, we see that alpha has high ionizing power, low penetrating power. Beta is moderate on each of those. And then gamma finally has low ionizing power and high penetrating power. So kind of depending upon what you're trying to do would determine which of these you would want to use. So when we think about alpha, that is thought of as the helium nucleus, which we see down here on the right. Once again, high ionizing power, low penetrating power. The beta particles are smaller than alpha. Since it's smaller, it has the ability to penetrate in more, but it's less ionizing. Beta particle is typically a negatively charged particle. It is a negatively charged particle. And then finally, the last one is gamma radiation. So gamma, as you see, is electromagnetic radiation. So it's not matter. So it's slightly different than the alpha and beta. And it has the highest penetrating power, lowest ionizing power. In this photo, they have an example where they have cesium-137, and it's a gamma emitter that's used in cancer treatment. So the gamma radiation you see that a lot in medical stuff. And it's because of that high penetrating, low ionizing. If you think about it, you don't want something hitting you that's ionizing you. That might not be a very good thing to have happen. But the penetrating has value. Okay. So a guy named J.J. Thomson put forth what they're calling the plum pudding model. So I always think this is kind of funny, but okay. He proposed that based on the stuff that Dalton said and then the stuff that was learned after that, he proposed that what you have is you have a big kind of blob of positive charge, and then there's negative electrons kind of stuck in it. Okay, so maybe he's right, maybe he's wrong. Except then some more experiments were done, and a guy named Rutherford used those alpha particles that we talked about just a moment ago from the radioactivity type work. He used that and he did an experiment. And so he had a beam of those alpha particles and he shot them onto gold foil. And then around the gold foil, he had one of our friends, a fluorescent screen, which would detect stuff that hit it, okay? Well, the expectation was it should just pass through and then just be detected on the back end of this circular detector. Most of the particles did that. Most of the particles went through and then didn't do any scattering, which is what they call that. But some of them did. And so some of the particles, some of the alpha particles didn't go straight through. They kind of they reflected, deflected off to the sides. And then it became, well, what in the heck's going on? Well, that's what got people thinking about the nucleus, is that obviously these particles were hitting something and then scattering, but they didn't hit it every time. So what's going on? Okay. So what Rutherford proposed was that you have a very small, dense, positive center, and then the electrons are all on the outside. And the other thing he proposed is that when you look at the atom, most of the atom's volume is empty, okay? And so if we look at this drawing on the right here, we see kind of like a drawing of what that atom would look like. And in the middle, we have the nucleus. And the nucleus is where the protons and neutrons are. And then the bigger volume, that's where the electrons could possibly be. Okay, and we'll talk a little bit more about that a few chapters from now. But the electrons are kind of moving around. They could be anywhere in there. Atoms themselves are pretty small, 1 to 5 angstroms. Angstrom is 10 to the minus 10th meters, so it's pretty small. But the nucleus is even smaller. We see if we're saying the atom is 1 to 5 angstroms, that nucleus is 10 to the minus 4 angstroms. So tiny relative to the whole atom. Through this process, that's where they figured out the protons and neutrons that were in that nucleus. And so now we're getting a better picture. We're getting a better picture of the atom, knowing that there's this nucleus in there that is protons and neutrons. Kind of around it is like a cloud of electrons. The electrons are moving around. And that gets us close. That gets us pretty much to what our knowledge is today of how things are. So let's talk about this a little bit. The charge of electron, minus 1.602 times 10 to the minus 19 coulombs. Proton is that same number, just positive. That quantity is called electronic charge. And we don't talk about that much ever. We talk because it's been defined that rather than working coulombs in that, when you talk about this charge, you talk about multiples of that. So instead of saying the charge is that value, you say it's +1 or -1. Okay, there can be other charges as well, but it's always those simple whole numbers. Neutrons have no charge because they're electrically neutral. So the protons are plus, the electrons are minus, neutrons neutral, so no charge. Every atom has the same number of electrons and protons, and that's so that you get a balanced charge. So if you're saying that you have the atom there and there's no charge on the atom, then the only sources of negative and positive are protons for positive and negative for electrons. Then the electrons and protons have to match up in terms of numbers. Then once again, as I said, 1 times 10 to the minus 10 is the definition of an angstrom. And when you talk about atoms and kind of these types of measurements, you almost always talk in terms of angstroms. So that's another thing you guys can memorize, what an angstrom is. As I said, protons plus 1, electrons minus 1. They have charge, neutrons are neutral. The big thing about these subatomic particles, and this table is the key here, is if we see there, we have proton, neutron, electron, we have the charge, but we have the mass. And the mass of proton is essentially very similar to the mass of neutron. There's a slight difference there, but they're both about 1. The interesting thing is, look at the mass of the electron. 5.486 times 10 to the minus 4 atomic mass units. And atomic mass unit, as you see up here, is defined as 1.66054 times 10 to the minus 24 grams. So once again, we don't do much with that number. We talk about atomic mass units, or AMU. The big thing you see here is that we said the nucleus had the protons and the neutrons in it, right? And we see that that was that little tiny dot in our picture. And then we had that kind of that electron cloud. The other thing we see, though, is the electrons really don't weigh much in comparison to the proton and neutron. So the mass of the atom is really pretty much all coming from the proton and the neutron. The small contribution from the electron, but relatively speaking, it's not really that significant. So the protons and neutrons are sitting there in the middle, in that nucleus. The electrons are in that kind of cloud there. And they draw it as a cloud, but really what that represents is the electrons are moving around. And there's mathematical ways to predict where they're at, and we'll talk about that a little bit later. But in general, that cloud just symbolizes that it could be anywhere in there. Okay, let's talk about atomic numbers for a moment. So we'd like to have some way to determine which element an atom is. And that's where the convention is atomic numbers. An atomic number is the number of protons in the nucleus of the atom. If something has, say, 6 protons, how many electrons would we have? We'd have 6, because if we have 6 protons, that's a plus 6. We want to get to neutral, so then we'd have to have 6 electrons to cancel out that charge and get to net charge of 0. So atoms have no charge overall, so the protons always equal the number of electrons. So one way to write the elements is with this convention. So we have here carbon. We see the capital C. That's our symbol for carbon. Then we have the 12, which represents, that superscript represents the number of protons plus the neutrons. That's the mass number. Remember, we said the mass of an atom is the number of protons plus the neutrons. That's where all the weight comes from. Electrons, we're saying, really don't contribute much. And then the atomic number is the subscript here, in this case 6. And that tells us it's how many protons are there. And by balancing charge, it also tells us the number of electrons. So just with this little designation here, a C with a 12 and a 6, we get a lot of information. We get another thing too. Can anyone tell me how many protons would be there? I mean, how many neutrons would be there? 6. How did you know that?
12 minus 6. So it would be 6.
Yeah, exactly. So we know that mass only comes from protons and neutrons. So if that's 12, and the atomic number, which we say is the number of protons, is 6, then as you said, 12 minus 6 gives us the number of neutrons there. So we can, from this little symbol here with the 2 numbers on it, we know what element it is, we know how many protons are there, we know how many neutrons, we know how many electrons. So a lot of information from a little thing that we've drawn here. Okay. So one thing you'll learn about chemistry is it's never that simple. Okay, there's always something else which you got to think about. And so atoms of the same element can have different masses, and we call that isotopes. Let's look down at the table here for a moment. And so here we're focusing on carbon. And what we notice is that there's 4 different isotopes for carbon, 11, 12, 13, and 14. 12 is the most common. That's like 99% roughly of the carbon is that. The others are less. Carbon 13 is the one you hear about when they do carbon dating for like archaeology stuff and all that. But what you notice is they all have 6 protons. And by association, since it's neutral charge, no charge, there has to be 6 electrons. That never changes. If it's carbon, it's going to have 6 protons. That doesn't change. But we said we've got isotopes. So if we've got different isotopes, what changes? The neutrons. And we see over on the right here, we see 5 neutrons, 6 neutrons, 7, 8. We see the number of neutrons changing. So we said before that that superscript is the mass, it's the weight, right? And so if the protons are staying the same, because they're always going to be the same, the electrons are going to be the same because we're balancing the charge, then the only way to get mass increase is to have the neutron increase. So that's what you're seeing when you have isotopes. You have different number of neutrons, but the same number of protons. And that's true whether it's carbon or anything else that has isotopes. Just about everything has isotopes, some more than others in terms of abundance. And that's what you call the amount of those different things. You call that the abundance. But almost every element has isotopes. We mentioned earlier a little bit atomic mass units, or AMUs. So as we said before, atoms, the mass is really a small number. And here they're saying that the biggest mass that's known is 4 times 10 to the minus 22 grams. So once again, so we don't have to worry about talking about these little numbers all the time and writing them out. There's a convention called atomic mass unit, AMU, and that serves as the base unit. 1 AMU equals 1.66054 times 10 to the minus 24th grams. We won't be talking about this minus 10 to the minus 24th or 10 to the minus 22nd of that. We'll be talking AMUs. So when we talk molecular weights and things like that, we're not talking the actual weights. It's based on this convention. So when we mentioned before that carbon had 4 different isotopes. It's mostly carbon-12, but there are the other ones. So which mass number do we use if we're going to use carbon as in a calculation, say to figure an atomic weight or molecular weight or something like that? Well, what is done is you calculate, typically calculate an average mass using all the isotope information that you have. So those atomic weights that you look up in a table are based on this. And what they do is they take the isotope mass times the fraction of natural abundance for each of those isotopes, do that math, and then add them all up. So you have the summation, you can see the summation thing in the formula there for all the isotopes. And then what that value is, that average value becomes what the atomic weight is. So in the carbon example, you'd have the 12 times 0.99 plus the 13 times, I don't even know what it is, but say 0.0002, and then for the other 2 as well, and add those up. So by convention, the masses of any atom are compared to carbon-12, 6 protons and neutrons being defined as exactly 12. Yeah.
Will we ever have to write out that equation?
No.
Because I learned it a different way to write it. So
Okay. Yeah. All you're doing is you're just accounting for the proportions of each one. Okay. That really becomes significant, and we'll talk about it a tiny bit in something called mass spectrometry. Because in mass spectrometry, you leverage these isotopes to kind of figure out what's going on. In normal stuff, you usually don't worry about it too much. And just on here, there's actually a mass spectrum here. So I'm going to just talk about this briefly, just I wouldn't worry about it too much, but you can figure out atomic and molecular weight by using a mass spectrometer. And here's a picture of one type of mass spectrometer. What I would just point out here is that you have an ions flowing through it, and then you use our old friends electric fields. You see the positive, negative, and you see magnetic field to move things through, to deflect things. And based on that, you can figure out, in other words, here's chlorine, for instance, 35 and 37 are two of the isotopes for chlorine. You can actually figure out how much chlorine 35 and chlorine 37 is present by doing something like this. So the only reason for showing you this is that the size of the peak, these are called peaks, that would be reflective of the abundance of how much is there. So it gives you a feel what the ratio of these two chlorine isotopes are. And just that some of that early work that we showed where they used charged plates and they used magnets to kind of move things down and figure some of that out, that's continued to be refined and used to figure out atomic weights and molecular weights. And this is a real common technique that's used these days. Okay, let's talk a little bit about the periodic table, and we'll spend a few slides on this. The periodic table is just the elements arranged in order of their atomic number. What did we say atomic number was? What is that reflective of? How many protons, right. So this is telling us hydrogen has 1 proton, helium 2, lithium 3, on down the line. So great, it's organized. That's, it's almost like if we were to organize you in the room by height or something like that. Great, we got a way to organize. But turns out there's a little more to it than that. When we look at a periodic table, usually they write things a little different than that way I showed you before with the atomic mass up as the superscript and atomic number as the subscript. Usually in the periodic table, you'll have the atomic number on top. In this case, for potassium, it's 19. And then the atomic weight is 39.0983. So let me ask you this. Based on that information, how many neutrons does potassium have?
About 20.
About 20, right. And you get that because you know the atomic weight, let's say it's 39 for the sake of this, to make the math easy. And we know the atomic weight is the amount of protons and neutrons together, because those are the things that have the weight for an atom. The atomic number, we said before, that's simply the number of protons that are present. So if you take 39 minus 19, you get 20, and that tells us that that other 20 mass comes from neutrons. So this is a handy way, just as before, some of the things of writing things tells quite a bit of information. That 39.0983, you get those other digits there, and let's think back to significant figures and measurements and measurement tools and all that. You get those other figures because it goes back to the isotopes. Remember we said, instead of it being just one weight, there's other weights involved, and then proportions of that, and we have to do that formula that we looked at a couple slides ago. So that's why you see some of these numbers that aren't exactly maybe what you would think. Those are the average of all the isotopes, taking all the isotopes into account. So let's take a look at the periodic table. There's a couple things that we want to point out. So the rows are called periods. So you see on the left there, 1, 2, 3, 4, 5, 6, 7. Those are the periods. The columns are called groups. 1A, 2A, then 3B, then you go over here to boron, and it's 3A, 4A on down the line. One thing that has changed in my lifetime, for the longest time, you always said 1A, 2A, 3B on down the line like that. Now a lot of people have switched over to just calling it 1, 2, 3, 4, 5, 6, 7 on down the line. I'm not certain what year exactly they started kind of making that change, but for me personally, I still call them 1A, 2A, 3A, 4A, and all that, just because that's how I was taught. But either way is correct. The other thing that you find is that the groups, the columns, those things tend to have similar chemical properties. So while the periodic table is nice because it kind of organizes things in order, but it turns out that the groupings work out so that, for instance, if I know something about sodium, but I'm not that confident about potassium, and I see they're both in the 1A column, the stuff I know from sodium is going to be similar for potassium because they're in that column. And that's something called periodicity. And so what that means is, and I think we got a slide here, yep. You know, when you look at these, and they have this, it's written out kind of funny here, but you'll see like helium, neon, argon, the kind of purple ones, 2, 10, and 18. Those are all non-reactive gases. Well, they're in that same column together. You see lithium, sodium, potassium, that's in that 1A column. They're all reactive metals. So if you know something about lithium, it's probably going to be similar for sodium and potassium and some of these things. So this is the periodicity that they talk about, is that by looking at a periodic table, depending upon what row it's in, what column it's in, a lot of times you can get trending information of how things behave. You can get similar property information, things like that. In terms of the rows, there's a lot of things that properties that as you go across the row, they either increase or decrease. And so you get some information about that. So the periodic table is real useful in terms of trying to figure out an initial guess at the properties of a compound or an atom or things like that. Okay, I think we're going to end there for today. Wednesday will be the quiz. We'll also continue on with chapter 2. Quiz is only on chapter 1. All right, thank you.
If you want to select on our table.
Yes, please, yeah.
Thank you.
Bye-bye.